Okay, so we were talking about complex numbers, and we have this nice image, in my opinion, where we have the real numbers, so all the nice numbers that we know, irrational, rational, relatives and integers, whatever, and then we introduce this extra line with a special number, I, and these are the imaginary number, and we call them real number. Real number. Okay, we know that real and imaginary. We know that there is 1 and there is -1, and these are connected by I by this simple equation definition, which is an equation as well. But anyway, so -1. Okay, good, good, good. But of course, they need to be numbers. So let's now think about only imaginary numbers for a second. Let's see if they are numbers. So if can I sum two i's together? Yes, I can. And I get another number, imaginary number, which is 2i. So can I multiply a number I by another number, for example, a fraction, or 0.5i? Can I do 0.5i? Can I do a square root of 2i? Yes, I can. I can put it 0.5i here, which is exactly halfway through 0.5i. Sorry, 0.5i. This is easy. We just stick the I as a coefficient in front of the number to remember that it's imaginary. We can divide by the same token, and then we can multiply by using this rule, remembering there is this minus that pops into sorry, pops into existence once in a while when you multiply numbers. So okay, it looks like we have the same situation as relative numbers, with this fancy symbol I stick next to each real number. Um, in fact, we can now define finally what is a complex number is. I'm sorry if it took long, but let's define a Z number, complex number, and the symbol is, by the way, this is C, which is the union, I think, or I think it's technically the union, yes, of imaginary and real number. And if you like, I'm not sure if this is customary, I real number, real number. But anyway, it's the union of these two sets. Okay, so these two together, the union, call it as whatever you like, the union of these two sets. So the complex number should be, I will give more details for the mathematician aficionados, and if it's not precise, forgive me, but intuitively is the union. And the only point in common that they have is 0. In fact, if you multiply 0 times I, you get 0. And this is the point of contact between the real and imaginary world, let's say. Now let's back to Z. So Z is in, this is in, it's in the set of complex number, when can be written, and now we have to leverage from the definition of vectors. If you remember, vectors are pairs written like this, vertical, but there is no fancy rule with the I. These are real numbers. Vectors is R square. In fact, is equal to R over R. There is no I. It's different, right? There is this special rule here. Still, a complex number is made of two parts, A plus I B. We cannot cross the bridge. They live together. So as a complex number can be any, and it's written, and I will try to give an example why this is the case. You can think about it, as, but there are many differences. You can think about a z number as a complex, as a vector, roughly, AB, where A is this number here, here, and B is somewhere here, and AB is exactly this point here. This is our Z. But it's not a vector because there is this I that plays a role, okay? So we need to keep them separate. And this what makes a C, the set of complex number, a field and not a vector space. So it's not a vector space. There is no okay, I don't know all the differences. I should study a little bit more and refresh my math. But trust me on that. There are plenty of differences between vector spaces like R square and complex spaces like C. And you can solve many problems as one easily you can see is that you can solve now x squared plus 1 equal to 0 easily because x, but this is kind of a cheat, right? X squared minus 1, but we know that x is plus or minus I now. This is the way to solve it. And this way you can solve every, and this is a big impact in the math world. Not to know about all the details, but you can solve any actually polynomial equation, even bigger than quadratic, and you will have exact the same number of equation in the complex field. So if it's square, you will have 2 complex number. If it's cube, 3, 4, and etc. Sorry. So yes, so the complex number allows you to solve any quadratic polynomial equation with the correct number of roots, the co-roots of solution, with the same as the exponent that you place there. Okay. How about real numbers? Okay, as you can see, every real number can be thought as a complex number quite easily. If you remember that 0 times I is 0, you can always think about, if you want to complicate your life, but you can, 2 can always be thought as 2 plus I 0. So a real number is a real number plus a 0 imaginary number. Okay. But this is interesting because how do you sum to, we remember that we need to deal with plus, minus, dot, and division. So how do you divide, how do you sum to complex number? Easy. You sum the 2 real numbers as you would do, because otherwise it wouldn't work for a real number. Plus I, you sum 2 imaginary numbers together. You know that we can sum imaginary numbers together. We did it here, up here. You know that can sum real numbers together, and we keep them separate because there is this line that is green that is, let's say, different. This could be plus or minus, plus or minus. Now, it's a bit more, so now I have to give you, I don't have a simple, I don't remember how to multiply complex number, but I should be able to work it out. So, what do you say? If you have z1 times z2, yes, it's easy. Oh yes, sorry, we do it step by step. A plus IB times A1 plus IB1. These are the two numbers, and this is Z1, and this is Z2. Now, we go term by term. We already know that we can multiply a number times I and we get the same number times I without the dot, if you like. So, and we know how to multiply. Okay, let's call it A1 and A2. And we know that real numbers behave like real numbers. So the first component of this multiplication is the first term times the first term, A1 times A2. And then there is the first term times the second term, which is I A1 B2 plus I B1 A2 plus we have I times I B1 B2. But we know that I times I is minus 1. Okay, so this gets flipped with the signs minus 1. In total, we get two real numbers, which are if you give me a sec, let's do it this way, A1 A2 minus B1 B2. Okay, plus I, there are two imaginary numbers, which are A1 B2 plus A2 B1. Okay, so as you can see, even though it's written badly, and I will rewrite it here, up here, we can see that the multiplication of two complex number, it's again a complex number with two real number and the symbol I that divides them, that separates them, not divides, separates. B2, B1, A2. Okay, so this is the new A, let's call it A3 plus IB3. As you can see, since as these are real number inside the parentheses, you can sum them easily. You get another number, B3, whatever it is, A3, whatever it is. It doesn't matter. At the moment is just a label. And this is another real number. The difference between two multiplication of two real numbers is a real number, so A3. And there is an I, and we keep them. And as you can see, this is called Z3. It's another complex number, and it's still, so now we can do the same with the well, let me do one step. For the division, I will introduce an operation that is important in complex number. But let me just pause a second and recap what we said so far. So we know that complex number are the union of two sets, imaginary number and real number. Imaginary number are just the real number times I. I has these special rules. And now we are going to introduce another rule that I need for the division. So let me erase a little bit of the board. I'm sorry about that. And then I promise I will give you, after this, I will give you another, I think, interesting. I want to get to the end of the video. Ooh, I cannot erase easily enough. Okay, maybe because I'm loading the other file and it's slow. I see. I cannot do two. Okay, next time I'll have to pause the video and wait because it's basically exporting the other slides, which is a big file. Okay, anyway, doesn't matter. I'm sorry. All right, next time maybe I can put music in the background. to make the video even more heavy. But maybe more pleasant. Or think about it. Okay, so what about dividing two numbers? Let's do the easiest one, and then because I don't remember exactly how it works, I quite anyway. But I know how to do this one quite quickly. So hope quite quickly. So a plus ib1 divided a2 plus ib2. Of course, now if you remember from whatever arithmetic course you had, when you have a fraction, you cannot distribute the fraction if there is a plus in the denominator. We know that. The best you can do is to break it into pieces, but you still have the sum. And this is the same number. But okay, but we know that it makes sense for us that if we divide two complex numbers by the same number, we get 1. We want to get 1. But let's see if we can write this in another way. And as a multiplication to get 1. So which number do we need to get? We know how to do the multiplication. I will tell you in a second. There is a formula that I don't remember. Another way to do it is to find these two numbers and then derive the formula. Anyway, the trick is that you want to find that number that multiplied by itself is equal to 1, which will be the same as this will be z, and this will be 1 over z1. Because if you multiply these two numbers, you get the same as the division of them. Okay, it makes sense. So we know that this is ax minus by plus I ax plus by, right? No, ay and bx. Okay, now of course we want, what do we want? We want this to be 1, okay? So we want this to be 1. How do we do it? We do, so we have two conditions. We have ax plus ay and bx must be equal to 0, and ax minus by is equal to 1. We need to find a and sorry, we need to find x and y. There are two conditions. We can do it. So, oh, this is boring. Sorry, I should have studied a little and prepared, but let me do it once because I don't want to pause and start again, and then I will go for the cherry on the cake at the end, which is the very interesting part, I guess. So let's see if I can do it. So we can sum the two conditions, and we have that a minus b times y plus a plus b times x is equal to 1. And also, so we know that, and then we have ax minus by is equal to 1. Okay, so I hope I'm not making this a mess. No, I am making this a mess. But anyway, I don't remember how the other way. I don't want to do it now. I mean, it takes, I'm making a mess. I should have done it before. Let me give you the solution, which is actually easy enough to remember, and I can prove it. a plus ib. If we do x plus iy, that's the fastest way, I plus ib, and then if I multiply times a square, sorry, a minus ib, okay, and then we have, what do we have? We have a square minus b square plus a ib minus b a, which is 0. So we are getting there. This must be 1. Oh no, this is plus, sorry, because minus I times I is equal to minus 1 minus minus 1, so 1. So remember this. So this is a square. So if we divide by a square times b square, we get 1. So where do we put this? So we have that z1 times 1 minus z, and then we know that z1 is a1 plus b1 with an I, and then x plus I is equal to a minus ib, but divided by a square plus b square. Okay, so this number here, which is a bit complicated, is the when you divide, is the it's called the inverse number, and it's used to compute the, the division of complex numbers. So what I want to say is that, okay, so as you can see, it's a little trickier to do the division, but I want to introduce, but by doing so, we introduce two concepts which are important for the next slides, which is the complex conjugate of a complex number and the modulus of the number. So I will keep this number here because by doing the division or finding the inverse of a number, we, more precisely, we encounter both concepts. One is the complex conjugate. So let's have z, and which is a plus ib, and then think about what is a minus ib, which is, if you take a complex number z, if you flip let's call it z star, basically we flip the I, the minus IB. So basically we are flipping around the real axis, as you can see with this minus sign. And this is it's called complex conjugate, and it's important because when you do z times z complex conjugate, you get, we did it before, we can do it now, but it's a squared plus b squared, which is exactly this number in the bottom, which is called the modulus of z. Okay, so I'm just introducing two concepts that we already know. Okay, maybe the complex conjugation in the vector, if you think about vector, is somehow not a rotation but a reflection. It's another operation which exists in terms of matrices. But the other thing is that the complex modulus is exactly the same as the length Pythagorean theorem, square plus equal modulus square of a V number. So in fact, this is the, if you like, is the length of this number here is modulus z. um, by all means, in the sum that is always real, it gives you the extension of the modulus. It doesn't give you the angle, which is 8, which is of course cosinus over sinus equal tan over alpha. but basically it gives you the length. So you see that the analogy with the vectors is very close. But we cannot push it too much because these are actually numbers and they behave like numbers. For example, you can divide easily, or I mean, not easily, but if I would remember the formula, it would have been easier, but I was sloppy with my math, and anyway, forgetting about that, I will give details in the slide. But let's finish off because then I will do a video on exponentiation, maybe of matrices and symmetries, which is interesting. When I will talk about quantum mechanics, I will need this. But before talking about quantum mechanics, I want to make a video about Fourier transform and power series, those things like that. And for that, I need to introduce the last bit, which is the exponential form of a complex number. Okay, so we know, big blue, we know e to the x. Oh no, so, yes, sorry. Let's make this. Oh, but it's more complicated than that. Okay, so I will make a video on this. It's longer than that. So I will just give you a hint, and then I will make a different video for that because I mean it can take another hour maybe. So let me give you an idea. Z is a plus ib, we know that, but we just saw that a and b can be thought, since this a squared plus b squared is equal to modulus of z, they can be thought as the cosinus, and let's make them the modulus to simplify our lives. Like for a second, modulus of z equal to 1, so we take the unit circle if you like. So this can be thought as the cosinus of an angle plus I sinus of an angle. And I will go through the derivation. I don't do it because it's too long. Well, not too long, but I don't want to do it now. And this, believe me, it can be written in terms of a to the e to the I alpha, where alpha is the angle. This is fantastic for many reasons. And by the way, this is exactly as you can imagine. We know the exponential. For x is the same definition, applies for the complex numbers, and I will break it down to see where the cosinus sinus are appearing. And just to let you know, this is a very famous formula because if you stick in these numbers, e to the I pi, which is just blowing mind because this is irrational. It's the exponential of an irrational number to an imaginary rational number, gives you -1, which is a negative integer. Or if you like, you can even write e to the I pi over 2, which is even nice because there is 2 there. It gives you 1. Okay, just these simple formulas allows you to wonder how these numbers are playing with each other and turning out. But I will make a separate video only on this to understand this connection here, which is interesting also for matrices as well. Okay, I hope you liked it. I hope you enjoyed. I will link some documentation and see you next time. Ciao.